Well, the first step in evaluating a double integral is to rewrite it as an iterated integral. In other words, we're just given region R, but if I don't know something about the region R, then I don't know what to use as my limits of integration, so I need to do that. This function is just y over 1 plus x squared. And this is our region R, described by this picture. X goes from 1, 2, 3 to 4, and the upper bound is the graph of x equals y squared. Now, for what it's worth, when we evaluate this, we can say, well, if we want to use, here's what I do. I make a stripe across this zone here, right? Make a stripe across it. And the top part of that stripe is this function. Well, it's x equals y squared, but I want this to be a y limit. Since I'm making my stripe vertically, I need y limits at the top and bottom, so that would be y equals square root of x and y equals 0, and that's where these two limits came from, okay? And then if I started making that stripe here and stopped making that vertical stripe here, then I've described the whole region, and that would say x goes from 0 to 4. So from 0 to 4 for x. And that means I'll be integrating with respect to y first, so y squared over 2, and then integrating that with respect to x. So, shall we? It's continuing onward. Of course, you see the 1/2 y squared, and of course the limits for y goes from 0 to the square root of x. Well, the square root of x squared is just x. And when you put in 0, you get 0 in the numerator, so you get 0 for that. So what we just have is 1/2, and I know I probably should have put that 1/2 out here. I could have done that. According to one of those properties of integration, I could have done that. So I just need to integrate with respect to x, x over 1 plus x squared, x going from 0 to 4. And so it's not too hard to see if you make a u substitution, u equals 1 plus x squared, then du is 2x dx, so this half plus the other half you get from the dx gives us 1/4 ln of technically absolute value of 1 plus x squared, but we don't have to use absolute value because 1 and x squared are both non-negative, so when you add two non-negatives you get another non-negative, so ln of a positive, and that one's allowed. So if you put in the number 0, you get ln of 1 plus 0, which is ln of 1, which is 0, so therefore the whole answer is what you get when you put in 4. So 1 plus 16, 1/4 ln of 17 is the answer for this double integral. It might be worth showing you, and I wasn't planning on doing this, so I might show you that you can do this one the other way as well. And by switching the limits of integration and switching our order of integration, we still will get the same result. Well, I opened my big mouth and I got into this one. I gotta confess, I thought I would show you that we get the same result if we switch the order of integration and integrated with x first with respect to y. But it was such a good example to show you that sometimes, like this one, was a fairly easy integration to do. This one, look what happens. If you integrate with respect to x, we get arctan of x, x going from y squared to 4. I don't even want to write this next thing out because it would be too scary to even think about integrating. It would be y times arctan of 4 minus y times arctan of y squared. Well, I could probably do that with a u substitution, like u equals y squared, then I'd have du, well, du over 2, but how do you integrate arctan? That's not a trivial question either. I mean, I have to take you back through possibly integration by parts would get us arctan. I don't know. I might actually have to say, well, don't we have a Taylor series for arctan? We might have to get it like that. So this turned out to be very illustrative in the fact that if I tried to switch the order of integration and make this the top at 4 and this the bottom at x equals y squared, and then I start drawing these horizontal lines across it, I start at y equals 0 and quit at y equals 2, I get just a terrible mess. to try to integrate. And I kind of stopped right here because I thought, I don't want to do this. But let me illustrate for you. Here it is with dx first and dy second. And I got to confess, I'm going to do it the cheap and easy way. I'm going to let my software do it because I'm not going to do that integration myself. But here it is. Oops, sorry, here it is. Not there. I didn't. Well, I could do it there now because I accidentally erased all the other awful junk I had there. But it was terrible. I wouldn't ever want to do it that way. But if I did, I do get 1/4 ln of 17, like I knew I was going to get anyway. So it was nice and illustrative to show you that, oh please, don't do it in one direction, do it in the other direction. In other words, do dy and then dx. Integrate with respect to y first, then with respect to x. Otherwise, you get something pretty horrible, in which case I just resort to my software and not try to do it like this. Oh, awful, awful, awful.